Hi, it's time for another math easy solution. I'm going to discuss further into the direct substitution property for limits and basically prove it for rational functions. It's a simple proof. My last video I did it on polynomials. Basically, if I recap what this means, basically if f is a polynomial or rational function and a is inside a domain of f, or basically means if you plug in a inside f, you're going to get a value and it's defined. Basically, you'll get this. So you could just, for any limit like this, you could just plug in the x equals a into it and you'll get the limit. And functions with, and also I showed in my earlier video, I did examples on this. So basically functions with this property are continuous at a, like I said above, it's defined. So basically not all limits you can just directly substitute, such as this one here. You can't just put in this one here because you're going to get it divided by 0 and that's not defined. Then you can see my video link below on how to solve the limits for stuff like this. Now before I get to rational functions and just recap what they are, but before that let's just recap on a polynomial. Basically a polynomial is just written something like this, where you have a constant plus and then x times, x to the power of 1, etc. So basically you have something like this. These are just constants times x plus constant x squared, or so you could, up to xn here. So this would be a polynomial. Now I proved in my earlier video that the direct substitution property, you could just plug in a and you'll have this one here. So now if we look at rational functions, it's basically rational functions here. This one is just r of x here. All it is defined as a polynomial divided by another polynomial. So this one, p of x and q of x, these are both polynomials here. So now if we look at the proof for the direct substitution property, for this one here, all we can do is just take the limit as x approaches a of this r of x here. If we just write this down, the proof of this is straightforward. Then we're going to get limit as x approaches a of p of x divided by q of x. And now if we apply the limit laws here, so you can just break this apart into two limits, divided by limits. But this one also, I just want to make a note here, q of a is not equal to 0 right here. Yeah, so we're doing the case where the bottom is, you're not going to get a divided by 0 here. So if we don't have this case here, so now we're going to have something like this. And now this one from the, we're going to use is the earlier proof for the polynomials. You can just plug in the function there. So you could just plug in direct substitution for each polynomial, assuming q of a is not equal to 0. So we're going to get equals to now p of a divided by q of a, and this one just equals to, well, r of a, and thus we have the direct substitution property. And basically we just plug in x equals to a inside here. And so we're going to have limit as x approaches a of r of x equals to r of a, and there's a proof of that one there. And a quick example here, basically limit as x of this rational function x squared divided by x cubed plus 1. And of the bottom here, if you plug in the 2, we're going to get x 2 to the 3, which is 8 plus 1 is 9, so it's not going to be 0, so we could just plug in directly. So we're going to have 2 squared divided by 2 cubed plus 1. This equals to 4 divided by, this is 8 plus 1 is equal to 4 over 9. There's our answer. So we can just directly substitute inside. Well, that's all for today. Hopefully you'll learn about this direct substitution property. It's pretty straightforward. I just wanted to go over the proof just for completeness sake. And that's all for today. Remember, you can download these notes in the Dropbox link below, and stay tuned for another math easy solution.